In this video, we're going to continue looking at some specific examples of families of specific kinds of distributions in the discrete case. This one, we're going to be looking at geometric distributions. We're also going to be looking at Bernoulli distribution, which is actually where we're going to start. So in a Bernoulli distribution, we consider the experiment of rolling a single die in this example. We'll call it a success if we get a 5 or if we get a 6. We'll call that a success. Anything else will be called a failure. If it's a success, a 5 or 6, we'll let the random variable x be 1, and we'll let a failure, anything besides a 5 or 6 on the row, we'll let x be 0. So what's the probability of a success? We're going to call this P. What's the probability of a failure? We'll call this Q. What's the relationship between P and Q? And then make a graph and a table for this distribution. You should be able to figure this out. Press pause now. Well, if you're either rolling a 5 or 6, the probability of getting a 5 or 6 with a single die roll is 2 6, which reduces to 1/3. So P is 1/3, the probability of a success. The probability of a failure is 2/3. What's the relationship between P and Q? Well, P plus Q has to be 1, so Q is 1 minus P. Now let's make a graph and a table for this. Now there are only two x values here, 0 and 1, so there are only two x values in our table and only 2 bars in our bar graph. So when we graph our PDF, 0 has probability 2/3, 1 has probability 1/3, and there's our bar graph for it. And of course there's our CDF values as well. That's called a Bernoulli distribution. So in general, a Bernoulli distribution is we divide the sample space into two outcomes. One we call a success and the other a failure. Okay, before we go any further, don't put a value judgment on those words success and failure. A success means we successfully got whatever it is we're counting. Does not mean that's a good thing or a bad thing. It might be good. Maybe you're counting how many times you win the lottery. If you win, that's great. But a success could just as easily be getting a positive result on a test that for some bad disease. So success there means you got the bad disease. Not a good thing at all. Sometimes it's completely neutral. A success may be having a child that's a female. It's not necessarily better or worse than a male, but it's the one that we're counting at the moment. So that's why we call it a success. Not necessarily because it's good. Okay. Secondly, I want to mention the name Bernoulli. Bernoulli is named after, I think this is after Johann or John Bernoulli, but there's actually a whole family of Bernoullis that were very famous mathematicians, scientists who contributed to many fields, many subfields of mathematics, including probability and statistics, as well as calculus and various areas of physics as well. And so there are lots of different things named after the Bernoullis. There's at least 3 generations of multiple people in different generations that were very famous in this family. So anyway, going on here, so we divide the sample space into 2 outcomes. We call one a success, we'll call that S, the other a failure, F. Let x equals 1 when there's a success and x equals 0 when there's a failure. Little p is the probability of success, Q is 1 minus p is the probability of a failure. The graph of the PDF is just 2 bars, there's just 2 lines in our PDF table. The mean of the distribution, well, it's easy to figure out. It's expected value of x. So it's x is 1, that's a success, then the probability of success is p, plus the x value of 0 times the probability of a failure, which is q. Well, 0 times q is 0, plus 1 times p is just p, so p is the expected value. It's pretty easy to see that the variance is just p times q. Let's work it out here. The variance is the expected value of x minus mu squared. So x is 1, then the mu is p. We just figured that out. So it's 1 minus p squared times the probability that x is 1, which is p, plus put in x is 0. So 0 minus p squared times the probability that x is 0, which is q. Well, Let's see here. 0 minus p is negative p. Squared is just p squared. 1 minus p is another way of saying q. So this is q squared times p plus p squared times q. Now notice they both have a p and a q, so if we factor that out, what's left? Well, you take the p and the q out of this, that's left a q here, and the p and the q out of this leaves a p here. Distribute this to see you get back here. Now q plus p is just 1, so we end up with just p times q. So one instance of a Bernoulli experiment is called a Bernoulli trial. Now, Bernoulli distribution it's a legit distribution in and of itself, but it's mainly of interest to us because we would like to do repeated Bernoulli trials. Usually independent Bernoulli trials are actually used to create geometric and binomial distributions. In this video, we're going to continue to talk about geometric distributions, the main point of this video, and then we'll pick up with binomial distributions in the next couple of videos, 2 or 3 videos after this. So now let's look at a situation that leads to what we call a geometric distribution. So we want to perform independent Bernoulli trials until the first success happens. We'll let x be the number of trials until the first success. That's the basic setup on a geometric probability distribution. So let's take an example, and again we'll have the same kind of Bernoulli trial that we had set up earlier. So roll a single die and let either a 5 or 6 be a success. And we will repeat this experiment, repeat the Bernoulli trials until the first success, counting the number of trials along the way. Let x be the number of trials until the first success. And then when you finally get a first success, then that you've performed the experiment one time. It may take multiple rolls. It takes however many rolls it takes. It takes x rolls until you get a success. So what I'd like you to do is actually get a die out and actually try this. Or if you don't have a die, maybe use a simulator on your computer or your calculator. But I'd like you to roll the die and see how many times it takes to get a success. So for example, suppose I have a die here, I roll, I get a 4, okay, failure. I roll again, 2, failure. Roll again, 5, success. I rolled 3 times to get the success, so x is 3. I've actually done the experiment once, okay, and got x is 3. So what I'd like you to do is actually perform this experiment. Roll till you get a success, record what your x is. Then do that entire experiment 20 times. So you'll end up with 20 successes, but a lot more than 20 dice rolls more than likely. So make a table and graph of your empirical results in order to get an expectation of what the PDF graph should look like. Of course, it should be maybe not the same as what you get with only 20 times, but it should be kind of similar. Okay? Go ahead and do that and come back. Press pause. Well, if you did this, you should probably notice that your highest bar is 1, 2's a little shorter, 3's a little shorter. It may not be exactly that, but in general, the bars, at least in theory, they should get shorter as we go down. Your experimental results might vary from that slightly, and of course, it'll vary from person to person. So let's go ahead and work this out all the way here. Okay? So what are the possible values for the random variable x? Well, they can be any natural number. Can't be 0. You have to actually roll it once to get a success. But it could be 1, 2, 3, 4, 5. No halves or anything in between. But it does go on forever. There's no end to it. So this is an example of what we call a discrete but countably infinite. So this situation here is still a discrete case because the x's come in chunks at a time here. And we can count them, even though the counting goes on forever. Okay? Now, let's see if we can figure this out. So since the x's go on forever, we cannot physically write down the entire table or the entire probability tree, but we could at least start it off. Okay, so let's start the probability tree for this distribution and then use it to fill out at least the first, say, 5 numbers or so in the table of the PDF. So see if you can do that on your own now. Press pause. Well, hopefully you came up with a tree for the probability tree that looks something like this. At the first time you roll the die, you could get a success or a failure. If you get a success, the probability of that is 1/3. Probability of failure is 2/3. If you get a success, we stop, and that's the end of the path with probability 1/3. And notice there, x is 1. However, if we get a failure, we roll again, either getting a success or failure. When we get a success, we stop. And here we see that we rolled twice, so x is 2. And the probability there is 2/3 times 1/3, or 2/9. If you got a failure on the first and the second, then you roll again a third time. If you get a success, we stop. We see the probability is 2/3 times 2/3 times 1/3. Notice we have a q, two q's multiplied together in a p, so that's p times q squared. So 1/3 times 2/3 squared is 4/27. However, if we get 2 failures in a row, we could get a third failure. If so, we go again. We could get a success or failure, and so on and so on and so on. This goes on forever. But every time we get a branch stopping when we get a success. Well, if you look at this way the table's set up, or the tree's set up here, notice that every one of these probabilities have a p on the very last edge where we actually got our success, and the rest of the edges are failures, so they get a probability q. So you always get a p and a q to some power. The two powers have to add up to x. So this is p to the first times q to the x minus 1 is the probability function. And here's the table worked out, really actually not only to 5, but I actually worked it out further up to 10. So we have 1/3, then you have 1/3 times 2/3, which is 2/9. Then you have 2/9 times another 2/3 is 4/27. 4/27 times 2/3 is 8/81. Multiply that by 2/3, you get this. Multiply that by 2/3, you get this. And each time we're multiplying by 2/3, here's the decimal approximations, and here's the CDF worked out here, at least approximately. So notice by the time we get to 10, we were up over 98% of the way there. It doesn't actually, in theory, ever get to 100% because the K's could go on forever. But we're pretty close to 100% already with only 10 things. So if we look at the graph, we get a bar graph. So here's our first bar graph. Our first bar is probability P, which was 1/3 here. The next in Q is 2/3, so this bar is 2/3 of the height of that one. The next one is 2/3 of the height of that one. The next one's 2/3 of that. And so we're just repeatedly multiplying by 2/3, and we get a bar graph like this. Well, this is a graph of what we would call a geometric series. Okay, a geometric series is just an exponential series, which the domain is only the natural numbers. So if you kind of see that if you kind of connected these with the tops with a smooth curve, you get an exponential function like you're used to seeing. Now, but the bars never go completely to 0, but at some point they're so small we can't see them. So then the formula is pretty easy to write down. PDF of k is the probability that x equals k. Well, it's this p times q to the k minus 1. Remember, q is just 1 minus p. So again, there's the PDF of k is p. Probability of x equals k is p times q to the k minus 1. Now it turns out that the mean is just 1 over p. The variance is q over p squared, which means the standard deviation is square root of q over p. And the CDF then is the probability, CDF of k would be the probability that x is less than or equal to k, which you would take the PDF, p times q to the k minus 1, and sum it up from I equals 1 to k, that should say. And it turns out that that value, that reduces to 1 minus q to the k power. Now, to derive these formulas for the mean, the variance, and then this last step here for the simplified version here, they make use of the formula for the sum of a geometric series, and I'm going to omit the proofs of that right now, some algebra that we could do, but I don't want to mess with it at this point. So let's see if we can put some of this to work. Suppose that 1 out of 15 people test positive for a particular strain of flu. what is the probability that the fourth person you test will be the first one to test positive? See if you can work this out. Come back. Press pause. Well, if we let x be the number of times we have to test somebody until we get a positive result, and we assume that the probabilities is 1/15 every time we test someone, then this is exactly the setup for a geometric probability distribution. Okay, so the probability that's happening, the first success is exactly on their fourth trial, not before or later, is just PDF of 4, the probability that x equals 4. And remember, our formula is p times q to the x minus 1, so that's p times q to the third, 4 minus 1 being 3. P is 1/15, q is 4/15, so it's 1/15 times 14/15 cubed. 14 cubed is 2,744. 15 cubed is 50,625. So there it is, exactly probability as a fraction. But in practical settings, we normally would like to have a decimal or something. So here it is as decimal version, or about 5.4%. And you see it worked out here on a TI-84 calculator. You could probably also go ahead and hit change to fraction at the end here and I'm not sure if it'll work for that particular fraction or not, but it might. It turns out that this distribution is important enough that it's built in as a shortcut on the TI-84. Now check this out. This is pretty slick. So the probability of each person testing positive is P equals 1/15. And we're going to find the probability of a success on the first trial, the fourth trial. So that's just geometric PDF of P is 1/15 and X is 4. And here's some screens here, but let me actually just show you this on a calculator. So here's a calculator here. Let's just look just at the calculator. So the way you get there is you go to distribution. So you go second, variables, to distribution. This one's near the bottom, so it's easier if I just use up arrow. And I find it there. It's E. And it's a geometric probability density function, geometric PDF. Now remember, use PDF when you want the probability that x equals a number. Use CDF when you want the probability that x is less than or equal to a number. So if you've got the newer operating system on a TI-84, it's going to come up with this wizard here, and you put in the probability, which was 1/15, and you put in your x value, which is 4, and you go down here and hit paste, and it comes up with this screen right here. See a bigger version of it right down here. Now, if you have the older version of the operating system on the TI-84 or TI-83, that little wizard thing doesn't come up. You just hit, once you did distribution and you got geometric PDF, it'll come up geomet PDF, open parentheses, then you type in the P, comma, the X. You have to know the right order, P first, then the X value, close parentheses, and it will give you that. Okay? And there's the probability. Pretty cool, huh? Well, it works very similarly on a TI-nspire. So on a TI-nspire, let's do the same problem. You go to menu. Let's see, I want to add a calculator. So I've got a calculator screen. Now go to menu, and you choose probability, and then go down to distributions. And let's go down somewhere. There's a geometric. We have a PDF and a CDF. This one's a PDF because we want the probability that x equals 4. So you put in your probability, 1/15. You put in your x value of 4, and there it is. All right, so that tells you it. Okay. Now, let's do one with a CDF. So suppose, again, that 1 out of 15 people will test positive for a particular strain of flu. What's the probability that the first person to be tested positive will be among the first 7? So remember, x is the number of times you have to do this until you get the first positive result, the first success. Okay, and so here we want the first success at either be 1, 2, 3, 4, 5, 6, or 7. So that's the probability that x is less than or equal to 7. That's the sum of the PDF, which is this right here, but that's actually the CDF. So that's a geometric CDF. The way that of 7 with this particular probability. So the way that looks on the TI-nspire is GEOM CDF of 1/15th, comma 1/7. So the way the CDF works on for geometric on the nspire is it's probability, lower limit, upper limit. Okay, and so this says sum from 1 to 7. That's the limits on this sum, and this is our probability. The way it works on a TI-84 is spelled just a little bit different. It's GEOMET CDF. Still give it the P, and you just give it the 7. You don't give it the 1. It always goes from 1 up to that number. So here you see the screen here. Let's just do it on the calculator. So here we would go to distribution, go up arrow to geometric CDF. It's the one right at the bottom. We give it a p-value of 1/15th, an x value of 7. Paste that in, or again, if you don't have the wizard, you just type it in directly, and there it is. On the nspire, works like this. Just go to menu, go to probability, distributions, go down to geometric CDF, and it does have the wizard there, so it kind of helps tell you what to put in. 1/15th for the probability, lower bound is 1, upper bound is 7. But this is kind of nice because you could go from just from 3 to 7 if you wanted the probability that was somewhere between 3 and 7. And so there we go. So what about the probability between 3 and 7? Let's do that one. So we could go here and go probability, distributions, geometric CDF, 1/15th there. And let's do the probability that we get something between 3 and 7 inclusive. So the probability that 3 is less than or equal to x, which is less than or equal to 7, and it does it. Now, if I want to do that over here on the TI-84, I can get it pretty easily, but I have to, it's a little bit harder. Go to distribution, let's up arrow, geometric CDF. So let's do 7. This would be the probability from 1 up to 7, and I want to subtract off from 1 to 6 probability. So this would be, so subtract off another geometric CDF, and we want to go up to, let's see, actually up to, we want 3 to 7, so we need to subtract off 1 and 2. 1 and 2 there, and so that goes up to 2, and what's left will be from 3 to 7 there, same number, same number. So that's an example of a geometric distribution. Sometimes that can be useful in a real-world situation. And it's nice because we got a really nice built-in CDF and a built-in PDF on the calculator.